Humanity is looking for a new home, and for decades, that search has centered on Mars. It is the most accessible neighbor we have, fueling a cultural obsession with reaching the red planet. But Mars is a small, energy-poor world. Its gravity is so low that a lifetime spent on its surface deteriorates the human body. To survive the radiation and the thin atmosphere, colonists would likely be relegated to living in these types of underground tunnels. While Mars works as a scientific outpost, it lacks the physical requirements to support a thriving, surface-dwelling civilization. This side-by-side shows the volume of our nearest neighbors. While Mars is a fraction of the size, Venus and Earth are nearly identical. Venus provides 90% of Earth's surface gravity, the most important metric for long-term health in space. But Venus is the hottest planet in the solar system, with a surface temperature of 460 degrees Celsius, enough to melt lead. The atmosphere is 93 times denser than Earth's. Standing on the surface would feel like diving 900 meters into the ocean, where the weight of the 97% carbon dioxide air would kill you instantly. Venus is currently a hostile wasteland, but its size and gravity make it the only world capable of becoming a true second Earth. By applying engineering on a planetary scale, we can strip away the toxic atmosphere to reach the planet beneath. We begin by cutting off the energy source. This diagram illustrates a massive array of angled mirrors positioned between Venus and the Sun. These mirrors act as a solar sail, using the Sun's pressure to hold position while deflecting light away from the planet. Deprived of sunlight, the atmosphere begins to shed its heat. After about 60 years of shade, the temperature reaches a critical threshold of 31 degrees Celsius. At this temperature and pressure, the carbon dioxide in the air turns to liquid. The result is a global rainstorm of unbelievable proportions that lasts for 30 years, filling the low basins of the planet. As the cooling continues, these liquid oceans freeze solid. The pressure drops as CO2 is pulled from the sky, leaving Venus covered in rock-hard glaciers. The heat and pressure are gone, but the carbon remains. It is a planetary time bomb. If the planet warms up again, the glaciers will evaporate, and the toxic atmosphere will return. To make the change permanent, we have to remove the carbon from the planet. We can use mass drivers, electric rails that launch payloads without rockets. These would fire frozen blocks of carbon dioxide directly into orbit. This model shows how the ejected ice is collected. Instead of letting the carbon drift away, we gather it to construct an artificial orbiting moon. This clears the atmosphere and secures the carbon. It provides massive stockpiles for future industrial use and rocket fuel. With the carbon removed, Venus is a dry, nitrogen-rich desert. To support life, it needs oceans. We can find this water on Europa, a moon of Jupiter that contains twice as much water as all of Earth's oceans. Construction drones would be used to cut ice mountains from Europa's surface. Moving this much mass across the solar system is a massive logistical challenge, but it is possible using momentum exchange. Space tethers act like giant orbital slings. On one end, a tether orbiting Jupiter catches the ice and precisely hurls it toward Venus. On the other end, a Venusian tether catches the incoming ice and drops it into the atmosphere. To save energy, the Venusian tether uses the momentum of the falling ice to fling the remaining CO2 glaciers out into space. The ice falls as snow, eventually creating shallow oceans a few hundred meters deep. Venus now has the water and the pressure required to support biology. The final stage is making the air breathable. A Venusian day lasts over 2,800 hours, which would grill any plants we tried to grow. We solve this with another set of orbital mirrors. These create a standard 24-hour cycle of light and dark, providing the consistent energy needed for a biosphere to function. Trillions of cyanobacteria are introduced to the new oceans. They begin photosynthesizing, pulling nitrogen from the air and releasing oxygen. Once the oceans are fertilized, we can introduce complex life. Genetically engineered trees would be seeded across the continents, spreading into massive forests that finish the work of oxygenating the sky. Over several centuries, these biological processes transform the nitrogen atmosphere into one humans can walk through with nothing more than an oxygen mask. Eventually, the air becomes fully breathable. Venus becomes a world of blue skies and sprawling forests, home to billions of people living in the most Earth-like gravity in the solar system. Future generations will look at records of the toxic, 460-degree wasteland their home used to be. They will see the ancient data of a planet that could melt lead and realize how much was changed to allow them to stand on the surface. They will see a history of ancestors who froze the hottest planet in the solar system, shipped in oceans from the moons of Jupiter, and built a biosphere from a desert. Terraforming Venus is a project that spans thousands of years. It is a testament to what is possible when we choose to build a future that we will not live to see finished.